Charlie. I am taking it that you can hear me from the quieting down of the room. Only because her name was invoked yesterday, I will have to start with the really important topic of Taylor Swift, right? You saw that coming. And I apologize to any Swifties in the room. That's what they're called, right? The big fans. That I don't get it. I do not get the level of interest and the craze with Taylor Swift. I age myself because the only songs that I know are some of her country era songs, but none of the recent stuff. And the question is, what can we learn from that craze, and we can apply to transmission planning, because it is incredibly important. As we're thinking about this energy transition. How do we get that fire going for transmission planning? And I think there is some move in that direction, but I am counting on our panelists to really up that. And maybe our lanyards will serve as the bracelets as we go through these different talks, showing our bona fides on how we think about transmission planning. So some numbers just to get us started. IEA just published a report that's talking about the 15,000 gigawatts of renewables that are ready to go and get onto the system worldwide. And some of these macro studies, I think, are helpful for giving us context. And our job in this room is to take those macro studies and deliver, right? Make things actually happen. And they praise the progress that we've made internationally as we're going through this transition to meet climate goals and such. But they caution, right, that unless governments, private utilities, and all of us get our act together around transmission, that progress is going to be substantially hampered. Commissioner Clements on Monday made the same point, right? That 80% of the benefits of IRA, that incredibly important law, 80% of the benefits hinge on a robust transmission system. And even though we are making progress around transmission as we think about interregional planning and interregional transmission, right, we're still falling behind. So on an annual basis in the US for the last couple of years, we are building, approving 20 billion worth of transmission on an annual basis, which is great because that's exponential growth that we're seeing. But the question is that adequate? And is that the type of transmission that we will need to build? So as we think about this transition, as we think about the growing amount of renewables, right, we need to think about it in kind of different categories. The fact that there's just a ton of these resources, the units that are going to be in the system, which has its own complications for the queue and such. The fact that there's just a ton of megawatts has its own implications. The fact that there are IBRs have its own implications. The fact that they are variable has its own issues that we have to deal with. And as we think about interregional planning and interregional transfers and transmission, we need to start thinking, yes, about the multi-benefits of transmission, but more so the necessity of transmission. I think we need to change the language that yes, there is benefits, but it's absolutely necessary. And so as Bill will talk about in just a bit, we're thinking about how the regions can better rely on each other as we get a different mix of resources on the system, as they become more weather dependent, as we think about building and connecting a system that is larger than weather systems. What does that look like? And so Bill will get us kicked off with that, and then we'll jump into a specific example of a transmission facility, HVDC, that is actually trying to address this, right in the middle of the country, and is going across multiple BAs and is in some of the best wind resource areas. What does that look like? And so Henry will talk through that. Ebrahimi then will bring us here to California and talk about what does transmission planning look like here, and specifically how is HVDC considered in there. And the thinking there is that HVDC is likely going to be a major player in this transition. And we're not apologists for any particular technology, but I think we want to give all these solutions a fair shake. And that's part of what Ebrahimi will be talking about. And then Mike will round it all up, talking about the challenges of interregional planning. So Bill will kick us off, setting up why we need to do this and the study, the value of this incredibly important Act of Congress study. And Mike will round it off with the challenges and some of the opportunities for interregional planning. So with that, I'll pass it over to Bill as we have this wonderful discussion. I will say that the panel has gone through some evolution, and so your program will look different. I think that's just the sign of the dynamic nature of our industry and the fact that the system is changing. That's reflective in the panel as well. And so we're glad for where we ended up. It may not look like it, but there is over 75 years of experience in this panel. But I imagine over the next 5 years, the gray hairs will grow substantially because of the challenges that we have. But please welcome Bill onto the podium to kick us off here.
Okay, thank you. Good morning. I'm Bill Lamanna from NERC. Previously, before coming to NERC about 6 years ago, I finished a long 17 years at the New York ISO. Before that, the New York Power Pool. Before that, with the General Electric Company. Primary focus of my work at those organizations was either developing tools and performing studies for clients or for obviously the New York Power Pool and its transmission owners at the time, and then through the deregulation and the setup of the New York ISO. So this is a topic dear to my heart. Somewhat shocked that the order came out directing NERC to perform this interregional transfer capability study. So I'm going to give a very high-level overview because we're really wrestling with what does this order from Congress entail? What's it really instructing NERC? And not only NERC, but the ERO and the ERO enterprise, which includes our regions, who work closely with their entities, okay, in their geographical regions. So this is really set up not to be just NERC, but what we refer to as the ERO enterprise and really all of industry. And you'll see that throughout my talk, that emphasis. So a lot of people ask, go forward. Goes forward. I'll get forward this way. Okay, why? Okay, the Fiscal Responsibility Act refers to the direction of NERC in performing this study. And it directs us that in consultation with our regional entities and what's referred to as transmission utilities, NERC shall, that wonderful word shall, conduct a study containing 3 essential elements. First being calculate the current transfer capability between each pair of neighboring transmission regions. The recommendation of prudent additions to total transfer capability between these neighboring transmission planning regions that would demonstrably strengthen reliability within and among such neighboring transmission planning regions. And then also recommendations on how to meet and maintain the identified total transfer capability together with the prudent recommended additions. And that's about all they said on prudency. And so obviously a big component of the study that we're wrestling with now is how do we define prudency, and then how do we conduct and establish existing total transfer capability, and then what would be required to enhance that transfer capability if needed, and how to maintain it. The kind of a statement that NERC came up with is to kind of just to set the tone for these first few months as we set up the whole study. We are looking at just the transmission planning regions. You'll see that we're pretty much following the FERC Order 1000 definitions of that. So we need to recommend prudent additions to total transfer capability to meet future demand and strengthen reliability. NERC recognizes that strong and flexible electric transmission systems capable of coping with the wide variety of system conditions are necessary for reliable supply and delivery of electricity. NERC is engaging industry stakeholders to gather inputs, assumptions, and conditions and ensure the study comprehensive and inclusive of necessary information. So sorry to bore you with reading all that, but that's kind of NERC's overall, set the stage, not get ourselves in trouble. Looking back and saying something myself, also why NERC? Well, we were heavily involved with defining a reference document on transmission capability, okay, with all of our associated entities that just kind of set the stage how to perform transmission transfer capability studies way back in 1995. And this kind of serves as a foundation for that. But as you well know, transfer capability, there's a lot of different methods people use to calculate it, many different purposes for the use of that number once it's calculated. A lot of work done in simultaneous transfer capability issues, neighbor to neighbor to neighbor type issues. So one of our challenges is moving forward, not only specifically in this study, but overall in NERC and its performance of its assessments. How can we get some level of consistency between all the approaches among all the entities that will be involved in this study? Okay, that will be asked about. We're looking for a lot of input on the existing methods and then any potential improvements in those methods moving forward. Basically, a very high level step through of this overall study is, first of all, as I mentioned, we're going to determine the transfer limits in the current system. We're going to identify any resource needs, identify transfer limit increase, mitigate identified reliability violations, and see the impact on the system in the future. Okay, the first thing that struck us is the clearest thing in the order was that this study shall be delivered by December 2nd, 2024. So recognizing the limitations in time on this, there's been a lot of discussions with our regions, a lot of discussions with consultants already on how do we formulate the study in order to be able to complete it. Okay, and now a remaining 13-month period. Okay, task one is what is the transfer capability? Okay, we think we've got a good handle on that, at least to establish the near term present transfer capability, and then how do we translate that to out to the 10 years? And then a second task is what is the deficiency? Is there sufficient capability? If not, how much is needed to maintain reliability? Very little direction given there. That's something we're working vigorously on establishing it. If you're going to measure efficiency, you need something to reference against. What that is will be, how do you establish what sufficient means? Okay, and then of course, how do you put all that together to come up with the recommendations for, in task 3 is what is needed and what is required and in a prudent manner. Part of what this aligns with the present work we do at NERC and what we are long-term assessments and short-term assessments, where we presently do a combination of a deterministic analysis to measure resource adequacy through reserve margin type comparisons. And then we have a biennial probabilistic assessment that we performed, okay, for a long-term reliability study. And this has identified a drop in overall resources, but an increasing level of demand, driving up the risk in the system. We get a lot of questions about, well, who's all involved? Okay, the Canadians not being subject to the congressional order, however, they are participating in the study. We won't be looking at any inter-Canadian transfer limits. However, Canadian imports will be a big part of the analysis of the transfer capability, not only from Canada directly, but through the U.S. system and point south. Then we have the same with Texas. Texas is participating, but they're not subject to the FERC jurisdictions, but so we're not doing anything inside Texas. And this identifies kind of the regions that we're breaking down, how we interpret that transmission transferring entity from the order. And right now we're focusing on following the FERC order 1000 on these definitions. Okay, this just shows kind of how the study's been approached, given the magnitude of it and the extensive nature of it. We set up an executive leadership group, an advisory group, and a project team. Again, this is ERO. That includes the not only the NERC staff, but the regional entity staff, and then all of industry. So all these main groups performing the study, leading it on executive level, and advisory level, include people from all these entities. This is another defining how it's broken down. Phase 0, really, I don't know why this was labeled that, but step 1 is we're defining the study scope, assumptions, and scenarios. We already have heavy stakeholder engagement and participation in this. We'll only be increasing that throughout the study. We're getting ready to go out for data requests and build these study cases and identify the scenarios for transfer analysis. As I mentioned, what we presently do, we have a long-term reliability assessment, the LTRA. We plan to leverage that on how we build out the system 10 years and identify deficient and surplus areas. Performing the transfer capability analysis, we're going to identify thermal limits in a pretty exhaustive setup. We have engaged a consultant, and the regional staff and NERC staff will be heavily involved in a lot of thermal limit analysis. The voltage instability will be limited, just given the complexities and time constraints associated with that. Okay, and then in the recommendations, one thing, as I mentioned, we're really struggling with this identification of what prudent transmission additions means. Will it be solely on reliability, or and how much would economics be pulled into this? Obviously, economics can't be done on an extensive basis just because of the time constraints and also other issues associated with the performance of the study. And one of the big things is defining metrics for this identification of prudency. Was trying to think through and talking with a lot of folks, how much could this align with the present work in the industry on metrics for resource adequacy, transmission adequacy, system adequacy, whatever you want to say. Okay, this kind of shows again, another way of summarizing the 3 steps, 3 objectives. And I included this slide here mainly to talk about at the bottom, as we plan to do a lot of work on scenarios to bring in. Right now, we've boiled it down to 5. This is not the final decision. As I said, there's still a lot of discussion going on. We're going to look at the impacts of winter cold snaps, surprise, surprise, or regional heat waves, renewable drought. Okay, that's the wind and the solar as it goes from max capability to 0, incorporating any wildfire risk type things, and then physical cyber security attack. And a lot of this is geared to get more of a wider area look, in addition to that adjacent area to adjacent area type look that really is directive, which is foundational to it, but how much do we go beyond that for neighbor to neighbor to neighbor type transfers, and on a much more wide area, interconnection wide basis. I mentioned the time constraints of this. Final report, look for it. This is more in the November, December time period next year. Okay, that report will compile the study results and be comprehensive enough for good review and validation of the report, and then address a lot of feedback. We expect to have feedback all through the report. Again, it started already. We invited all throughout the study. Don't wait till the draft report to come out and provide comments then. Okay, and we need to submit it to FERC by December 2nd, 2024. Okay, just to expand a little bit is NERC's role. Some people say we were chosen because we are the independent voice for reliability. That's been our charter and mission for especially in the last few years, expanded out to looking at risk assessments. There's a lot of risk reports on our website talking about how to do risk assessments, the movement to expanding that to energy assessments, and then now this transmission adequacy type assessment. Not only does a study mean when it gets published, but what it means to the future moving forward and how we perform. We see this as critical to performing energy assessments. It is transmission system is a major constraint for the capacity to energy conversion to delivery to the consumer. We regard this as a critical assignment that supports our reliability assessment mandates that I mentioned, our short-term and long-term assessments. And we recognize as the transmission system, a strong one is crucial to the reliability of the system and the adequacy. I mean, the reliability is pretty straightforward. That's already exists in our TPL standards, but also the new term adequacy, whether you call it energy and transmission and resource and transmission or a system. And a big driver of this is obviously the rapidly changing resource mix, needs greater access and deliverability of those types of resources. They could either be remote, they perform differently than the present traditional resources. Okay, and we recognize this will probably lead to an ongoing assessment that will be critical to maintaining the BPS reliability. So I don't know if you want to take any questions now or defer to the panel session. Great. Okay. All right. Thank you.
All right, thank you, Bill. And Bill, of course, is giving us a preview of the work that they're going to be doing over the next couple of months. Incredibly important work that you can expect to come to a FERC region near you very shortly. And so this is an opportunity to see on the front end the discussion, how they're approaching it, and perhaps he'll be taking input from a group like this as stakeholder processes continue. We will have Henry actually go next. Thank you, Ebrahim. Ebrahim is just ready to go. And so we'll have Henry go next, and he'll be talking about a specific project that Invenergy is working on that lies right in the middle of the country. As we think of the amount of resources, we talked about what the IEA mentioned globally, but yesterday and the day before, we have 2 terawatts of resources in the queue at the moment that we are trying to unlock and really tap that potential. And how do we benefit from the diversity of resources across the footprint? So Henry, I'll let you go ahead and jump into your talk here. Thank you. Would you like to use this or the other?
Thank you. So, hey, it's good to see everyone. My name's Henry Abrams, and I'm with Invenergy. We're traditionally a renewable energy developer, but are now a transmission developer. And we'll talk a little bit today about why are renewable developers working in transmission and some of the projects that are being looked at in the country right now. So to get started, we'll kind of look at the energy transition in the US right now, the resources, the infrastructure. We'll talk about the potential solutions and why HVDC is kind of shining right now as a preferred option. And then we'll go into a case study of one of the such projects that's being developed. So to get started, looking at the US power system kind of from the developer lens, we see the wind and the solar resource down on the bottom. And we see it's not where the demand is necessarily. And there's not necessarily the transmission infrastructure in those regions to get the best resource out of there. So that's kind of the fundamental that's prompted a generation need for more transmission to keep building renewables as they're needed. And then looking at the existing generation in the US, you kind of see that the renewables are concentrated in the areas with the highest resource efficiency, more so than the areas where there's the load. So you see in the middle, there's most of the wind development in the central US, which was that rich resource region that was shown, but it also happens to be an area with limited transmission infrastructure. And then with solar, you see a lot of solar being developed in the south, southwest, southeast, where the solar resource is good. But again, it's not necessarily correlated to where there's demand. And some of those markets tend to be saturated as well. And looking at the transmission a little bit more, you start to see the regional nature of how a lot of the transmission is structured. So here's the ISOs in the US overlaid over the existing transmission grid. And you see kind of why there's all the renewable development kind of concentrated in these areas. And you see it stays in those areas. So the most wind solar penetration is staying in those areas with the highest resource efficiency. You see MISO, SPP, CAISO with the highest penetrations of renewables, or ERCOT as well. And so from our perspective, we're looking for solutions to get access to that great renewable resource in areas that may not necessarily have access to it right now. And that's prompted transmission projects and kind of the fundamental of why a generation developer is in transmission. Another benefit that kind of comes with this is when you think about extreme weather events. Extreme weather events are increasing in frequency and severity. And there's a couple of recent examples on the right where you see Winter Storm Uri, the prices in SPP skyrocketed, but remain relatively flat in PJM in MISO. And that's kind of a signal that there's a need for not just export and transfer of renewables between regions, but in severe weather events, there could be a benefit for additional transfer capacity to support things like this. And this was one example, and shortly after there was another example that you can kind of see with Winter Storm Elliott. And again, it just kind of highlights there's this opportunity for renewable generation projects to build transmission as a piece of them, and also provide a significant amount of support during system emergencies. And then that kind of prompts the next discussion of how do we do this, and what technology and what's the best way to support these goals. So looking at a few options, we'll kind of compare transmission solutions. So in the AC system, we've kind of picked, you could think about a double circuit 345 line, or on the other end of the spectrum, you could look at 765 kV AC. And then in the HVDC solution, we're looking at a HVDC bipole here, kind of point to point with 3,000 megawatt rating. And what you see is in short distances, often the AC solution is great. You see on the right there, kind of power transfer capability as the line length increases. And then the other chart, even further to the right, you see the cost of that power transfer capability as the line length is increasing. And what the chart on the right includes the kind of converter station, substation cost, and the line cost. And what you kind of see is for short distances, the AC solutions are great. When you start thinking about interregional long distance transmission, HVDC starts to shine as a more optimal and economical solution. So the break-even points are always changing as costs change, but this is a recent example using MISO's cost estimation guide. When you think about interregional, it's long distance, and that's where we really start to focus in on HVDC. So you kind of see, maybe going back here, we also have the right-of-way widths. HVDC, you can get a really compact right-of-way. So a 150-foot corridor, it looks closer to a 345 line than it does a 765 in a lot of ways. And so that's one piece. I think another piece is the electrical efficiency with long distance, avoiding the need for AC compensation. That's where the economics start to go in favor of HVDC. And you also get a lot of system benefits with HVDC. So things like reactive power and power flow control are inherent to the nature of an HVDC technology. And it really has become a preferred solution looking at these long distance interregional projects. Also, if you're thinking about the asynchronous interconnects in the US, HVDC is the option there as well. So when we're looking at an HVDC project, there's a few topologies. I think there's kind of the traditional point-to-point option that's thought about a lot. It looks like an offshore wind park in a lot of ways, where people are looking at an islanded generation system on one end and a load on the other. And it's kind of the simplest solution, but there's an opportunity to provide more system benefits with a more complex solution as well. And so adding, when you think about traveling these lines such long distances, there's opportunities to add additional connections. And there's opportunities to add connections back where the generation is as well. And that can start to build out this interregional backbone with HVDC. I think there's a key consideration, though, that this needs to really be considered in the early stages of design of these projects. So like in an AC line where it can be networked easier after it's built, you can add line breaks, things like that. It's not nearly as simple with HVDC. So when you're planning an HVDC project, you really need to make these decisions early on. Is it going to have additional terminals? Is it going to have additional stations? Is it going to be multi-terminal, or is it going to be point to point? Those are things that are crucial in the early stages. And as we think about planning HVDC in these projects, these are the kinds of decisions, like we kind of have to get them right the first time, because it's not as easy to change after the initial design of the project. I think adding additional connections also comes with challenges. So there's additional AC interconnection procedures. There's different technical requirements in each region. And when you're thinking about gigawatt scale projects, they come with gigawatt scale network upgrades with the injection. They're often treated as kind of generator interconnection requests. And so there's complications too in adding additional points. And so some of the ongoing projects in the US are highlighted here. You see there's on the left, the HVDC projects, existing and planned. And I think you see there's a lot of development going on right now. And then on the right, you see a list of projects that are determined as shovel ready to go. And there's a lot of projects that are also ready to go. I think that it shows there's movement, there's momentum, there's we're ready for building these HVDCs. And now we'll dive into one of these projects and a good example here. So this is the Grain Belt Express. It's an HVDC project that kind of originates in southwestern Kansas. And you see down there, there's great wind and great solar resource. And it's designed to provide access to that resource in other regions that otherwise would not have access. So that's kind of the one key piece of it. Another key piece is those regions will get access to renewables that are not necessarily correlated to the renewables within their region. So in MISO or PJM, through projects like this, you'll get access to renewables that may be on a different profile than those within your region. And that's helpful for, just your diversity of generation mix. And then also projects like this will provide the interregional transfer capability we're talking about. So in system emergencies, you can reverse power flow with HVDC. You can kind of provide additional benefits to the regions that are connected through these projects. And this is kind of what it looks like on a rough single line, but you see the converters in SPP, MISO, PJM, and that kind of interregional backbone we were talking about that can be provided through projects. Looking a little bit at the technology here, Grain Belt has gone with the 600 kV bipole HVDC configuration. It's got 345 kV AC interconnections on each side, and it's rated to deliver 5,000 megawatts of power. So a key piece here is you kind of see there's a set of about 2,500 megawatt converters, and there's two of those in parallel on the sending side, so that you're able to get a 2,500 megawatt delivery into Missouri and a 2,500 megawatt delivery into PJM. And these are the kinds of things that are fundamental to design of the project and really crucial in the early stages. With Grain Belt, we've selected Siemens Energy as the OEM and are working through the design stages there. And again, it's these decisions, these project fundamentals are they're fixed in the early stage of the project. We're using the voltage source converter technology, half bridge, and there's a few key pieces of that technology that are being advanced through this project. So the power and the voltage ratings are 5,000 megawatts, 600 kV. The multi-terminal aspect is another piece. You have those parallel converters in Kansas. You have this multi-terminal functionality that's being defined and developed and implemented through projects like this. You have a common question is when there's a DC fault, what happens? So all these things are, they've been implemented, but they're really being extended now through some of these more challenging projects that are being developed and executed. Additionally, the renewable integration piece is huge. So you think about a large renewable system being built and connected to these converters. There's control functionalities, there's coordination, there's all the system responses really being better defined and developed and advanced through these projects. So in summary, I think that if there's a few figures you walk out of here with in your mind, I hope they're these ones. It's, there's this need for interregional transfer, number one, both for renewables and for system benefits. There's projects being developed right now, HVDC and transmission projects that are ready to go. And then that the technology for these applications is capable and it's actively being implemented with the OEMs and in the design and execution of these projects. So I think there's a need, there's projects ready, and we're working through the implementation. It's an exciting time.
All right, thank you, Henry. I think that was a good example of building off of what Bill just discussed and the need for interregional transfer capability. And of course, the bill is not going to dictate what that looks like, but this is one potential way that could be increased. And yet in some ways, right, with the dozens of projects that are now being proposed and at various levels of development, it seems like it's somewhat of the Wild West when it comes to HVDC, right? What are the standards? What are the codes? How do we actually plan for these? How do we incorporate those? And so Ebrahimi at the California ISO is going to talk about the planning processes in California and how they think about transmission planning, how they think about HVDC, and I think eventually ties into the conversation of really tapping into the benefits of interregional connection and unlocking all the renewables that we're seeing grow in the system. So take it away.
Thanks, James. Good morning, everyone. My name is Rahimi, and I'm a senior advisor in transmission planning in CAISO. And the title of my presentation is HVDC Planning and Operation in CAISO. But before getting into that, maybe in a few slides, a high-level summary what kind of about the organization CAISO, and also our transmission planning process in California, the framework, how does it look like, and how these projects are being defined or introduced and being implemented. At a high level, California ISO is a balancing authority area and maintaining reliability on the grid, manages flow of energy. The part that I will be focusing on mostly is the third bullet, oversees the transmission planning process as a planning coordinator, operates the wholesale market, and also for much of the Western US is energy imbalance market, West Energy Imbalance Market, CAISO operates that, and also is a reliability coordinator for much of the West, RC West. This is kind of a high level, the map of the areas in the Western interconnection that CAISO is a reliability coordinator and starting in 2019. Some stats about California ISO is the peak load has been 52,061 megawatts as of, and it happened on last year, September 6, 2022. And that broke a record, which was there for 16 years. So the one before that was in 2006. The rest of the information is that the one number I want to emphasize here is the total power plant capacity in CAISO is 76,000 megawatts, out of which is around 33,000 megawatts are inverter-based resources, wind, solar, and storage. And this is a status quo where we are today, or as of August. We'll see in later slides where we're going to go in coming years. So just 1 minute on this, the framework, how transmission projects or in general planning is done in CAISO footprint per se, is that the load forecast is done by, provided to whole industry by California Energy Commission. The load forecast that CAISO uses is not developed by CAISO, it's California Energy Commission. Through their stakeholder process, IPER, they come up with the forecast based on policies, electrification, and energy efficiency, and so on and so forth. They come up with the forecast for coming years. That is an input to another process, is a resource portfolio, which is developed by California Public Utilities Commission. They are the ones considering the mandates on greenhouse gas emissions and electrification and so on. What resource portfolio will be kind of considered or assumed in our planning evaluations, right? How much in like 10 years from now, how much wind, solar, storage, and other resources will be in the system, both for resource adequacy to be able to supply the load and also to meet state objectives with regards to greenhouse gas emission or renewable portfolio standards and so forth. So those two are input to transmission planning process, load forecast and supply. And in CAISO role in transmission planning is how we can connect, supply the load through the resources while meeting the standards, right? NERC reliability standards, WEC regional criteria, ISO planning standard and so forth. So that's the kind of overall high-level framework that transmission projects are introduced. And most projects are kind of transmission projects are three categories. One is reliability assessment, which is, can we serve the load? Basically, is there enough capacity on the transmission system to serve the load and meet NERC reliability system, basically. Another group of projects is policy projects, is that based on the portfolio that CPUC provides to us, don't want to go in, what transmission enhancements are needed to make those resources deliverable based on certain definition. How we can make sure those resources could deliver their power to the load. Those are kind of policy-driven projects. And the last one is economic assessment or market efficiency. It could be reliable and meet the policy, but if we implement a transmission project, then overall production cost simulation shows that it could be less cost for consumers. So those will be kind of called economic projects or market efficiency projects. I guess Danielle yesterday in her presentation mentioned this is an annual transmission planning process CAISO does. In last year, if you combine those three groups of projects, there are 45 projects approved by California ISO between the three, with an overall cost estimate of $7 billion. And several of them were policy assessment to transfer renewables to the load centers from where they are. I guess, again, Daniel went through this. I just shows how these entities, PUC, CEC, and CAISO, are working together to have better coordination between the three, in not only in transmission planning, also in interconnection process, in resource procurement, and so forth. So more on that will come later in future discussions. So anything I explained earlier on it is a planning process is based on mostly 10 or 12-year planning process. And any enhancement identified earlier, they call it actionable. So someone will be responsible for implementing those projects, funding them, building, owning, operating, and so on. It could be incumbent PTOs. It could be competitive procurement through process will do that. Starting 2 years in 2022, CAISO developed its first 20-year outlook. So this is not kind of actionable or is not based on CAISO tariff. It's just provide a longer-term outlook on considering the evolution in resources and demand and electrification and all of that. When you look very long-term, 20-year, how does it look like? What transmission kind of concepts would be needed to serve the load, transfer the resource, and so on. The link is there. The first 20-year outlook was posted in May 2022. I want to show that the same 10-year is actionable projects. This is providing an insight to, or a kind of directionally where we are going when we plan transmission. Currently, we are in the process of developing our next 20-year outlook and update to the previous one. And this slide, I'm not going to go through detail, but shows that the resources we received at the very column at the very right, for update to a 20-year outlook, what resources are assumed in 2045. So again, not going through all of them, but at a high level is around the 70 gigawatt of utility scale solar. It's around 20 gigawatt of offshore wind, which we come back later on integration of that. 12 gigawatt of out-of-state wind, and around 50 gigawatt of battery storage, 4-hour battery storage, and more kind of on 8-hour or longer term duration. So all in all is around 165 gigawatt of resources, wind, solar, storage, and different combination, in a state, out of state, and so on and so forth. That's kind of in the long term, how does it look like? Now, with that background, we come how HVDC comes into the picture. Why is it being considered in CAISO evaluations? So currently, there are 3 HVDC projects active in California, not in CAISO system, those who are familiar. So there are within California, there are some kind of CAISO manages 80% of the load. There are 20%, but LADWP is smart and others that they manage the load. But physically, there are 3 projects in California. One is PDCI, which is the capacities are there, and CAISO has a scheduling right for 50% of that capacity. Transbay Cable is a voltage source converter HVDC project with NMC technology, which predominantly delivers power to San Francisco area. An Intermountain Power Project, it delivers power to LA, LADWP system. How the operation works on this graph, the one on the left, shows how PDCI is operating, Pacific DC Intertie, which is connecting Northwest to California. And on the diagram on the left, this is 2022 on March. And then those are different percentiles, right, from 0 to 100%, and the solid line in the middle is median, 50%. It shows that in the middle of the day, as the solar in California increases, the level of import, how much power coming from Northwest goes down. And then in the middle of the day, it's a kind of negative. Actually, power will go from California to ship solar to Northwest. This is in March, which load in California is relatively low, and there is a significant solar generation. The diagram on the graph on the right is September in 2022. That's when CAISO broke the record maximum load. And you can see that for most of the day, we are importing energy from Northwest. And the ramp, you see the small morning ramp that more energy is needed in short time. And a kind of a 3-hour evening ramp, more power is imported. So the from operation perspective, these are designed to from market perspective, the schedulings, right? Generations want to ship export power to California, they schedule on that, and then the market condition determine how much flow we have on the existing DC line on PDCI. Project under development in 2021, 2022 transmission planning process, the load forecast we received from California Energy Commission showed that significant load growth in the San Jose area. And to be able to serve the load, the forecast load, we looked at different alternatives, adding new AC lines or reconducting the purple lines on diagram are all 115 kV, kind of reconducting all of them or the ones that are showing lack of capacity. Considering battery energy storage or HVDC, looked at different alternatives, but considering pros and cons, I don't go into detail, but taking outages to rebuilding line is a challenge in that area given the load growth. And because energy storage, there was a lot of discussion yesterday, is in addition to short duration, 4-hour for now the existing technology, what we need to think about is the charging. Is the transmission system capable of, if you add a lot of the storage in a pocket, is there enough capacity in the evening hours to serve the evening load and charge a significant amount of batteries? So CAISO runs a study how much you can accommodate the storage in a certain capacity area to be able to meet reliability and charge the battery to be ready for the peak load the day after. So considering all of that, what the project that was approved and it's awarded and is being developed as we speak is 2 HVDC lines, basically bringing power from periphery of San Jose to downtown San Jose. And the ultimate configuration is, Henry touched on that, it's a multi-terminal. So the converters will be added at a later stage and connect these 2 DC lines on the DC side to make it multi-terminal as the load forecast keeps increasing. And the main driver for DC, these are not, I mean, interregional, of course. These are, the main driver was the need for flow control to be able to control the flow under contingency. So if it's AC line, you lose a trip, and then the line that recently is going to be overloaded. But with DC, you can control the flow under contingency condition. And potential for undergrounding, if you have underground, it's easier with the HVDC. And also with VSC HVDC, you get voltage support at both terminals, right? When you connect the DC, you get a STATCOM more or less in there. Again, to the point Henry mentioned, as we were developing functional spec for these projects, the multi-terminal feature was included. So if it's not done, later on you want to make it multi-terminal, there are some control challenges, the controls don't work, and so on and so forth. So it was anticipated in the function spec that at a certain point, this is going to be multi-terminal. Now the bidders, or project sponsors need to demonstrate how these links work if we're going to go and make a multi-terminal. So to that point. So other projects I want to talk about briefly is other HVDC projects that CAISO is considering. And before going into this detail, there is more HVDC projects in and around of California, which is CAISO is not planning. Some of you are familiar with Transwest Express, is a DC line bringing, Idaho wind and New Mexico, Idaho and Wyoming wind to the west. Sanzia, New Mexico. So there are DC projects that are being developed by, developers that bring eventually power to the west, but is not what CAISO plans. What I'm going to discuss here is HVDC projects that CAISO is considering. So offshore wind, the different levels if you go through detail, but based on the portfolio, CAISO is mandated to develop transmission to integrate around 1,600 megawatts offshore wind in north coast of this Humboldt area, as you can see. So the diagram shows that the existing transmission is 115 kV. There is not enough capacity. We need to develop transmission in north coast to be able to interconnect. In the Central California, Morro Bay area, there is 500 kV line, and there is a nuclear power plant there. And there was a discussion to retire in a couple of years. Now it's extended. So there's some timing around offshore wind development in the area and so on. And how we're going to integrate offshore wind in these two kind of areas, that's where HVDC as an alternative is something that we are considering. And not only accommodate the numbers like 1,600 and 3,000 existing, but also California has a goal of 25 gigawatt of offshore wind by 2045. How the solution fits in the bigger picture as we move towards that ultimate goal of that volume in the long term. So in Central California, just mentioned HVDC is being considered so that it could be an HVDC line from Diablo area to Northern California at a very high level to deliver power to Moss Landing per se, which delivers eventually to the Bay Area, which was one of the major load centers. Or it could be a DC line delivering power from Central Coast, Diablo area to Southern California, right? LA Basin and so on. If the volume of the offshore generation in total, nuclear and offshore wind or one offshore wind by itself goes beyond the capacity of the existing 500 kV system in the area. In North Coast, if we kind of look in the long term, the conceptual design is that to accommodate the 20-year outlook at the kind of ultimate goal that California had, we need a combination of technologies, right? We need high capacity 500 kV AC line to connect to the existing system. We need overhead HVDC lines to deliver power to kind of Bay Area on land, onshore. And we need the sea cable HVDC to deliver power. And then sea cable HVDC, which in the long term, the thinking is if we get into the sea grid, offshore grid, how would that look like? Do we need something like that? So that alternative is enable enables us to move towards C-grid if need be, if the technology gets there, some floating HVDC converter station, or the dynamic HVDC cables and so forth. That's the kind of the transfer path between offshore wind and the rest of the system. As when the diagram says, there is a lot to be done. Now you inject that much power to the system, how you gonna transfer it from that location to the rest? There is more to be done. But again, this is kind of conceptual level, what needs to happen to transfer that level of power to the rest of the system. HVDC definitely is an option. Next step, we are looking at 20-year outlook. I mentioned the technologies here. And on out-of-state wind, again, numbers was 12 gigawatt. HVDC is being considered. Do we want to put HVDC to deliver directly to the load center in California from out of state? Or we want to bring them to the border of the state, and now you have to develop a transmission to take it from that border to the rest of the system. Those who follow offshore wind development in California in kind of May next year, out of all these alternatives, one project will be proposed for approval because it's included in base portfolio of CPUC. And then again, the objective is DC, AC, and so on. Whatever that is, it should be able to have the flexibility to be expanded upon to as kind of more and more offshore wind is developed, and also enables the future technologies. That was my last slide. Thank you.
Great. Thank you so much, Ebrahim. And I'm glad to have a panel where we have NERC, we have developers, and we have the ISO thinking about transmission planning and kind of where we are going as a system and how we all need to be talking the same language and working together. So Ebrahim, thank you so much for that discussion. And so to round this off, Mike Spector is going to be talking about the challenges of connecting the different regions, what the opportunities are, and the perspective from Grid United. So take it away, Mike. Thank you.
Great. Well, thank you to ESIG and James for having me today. On your agenda, Chris Adlow is the CCO and CTO of Grid United. He got sick earlier in the week, so I'm filling in for him. So to use some baseball terms, I'm pitch hitting and also fourth on the panel, so I'm hitting cleanup. So I gotta finish up this panel strong. First off, this is a little bit of a confusing title. Challenges connecting the interconnections. And when we talk about interconnections, what I'm talking about is the Eastern interconnection, the Western interconnection, and ERCOT. We'll get to the challenges, but before I do that, I'll first give you an overview of Grid United, and we'll also talk about some of the benefits of interregional planning and interregional lines. Henry did a great job going through them, and I have some other benefits. So to tell you a little bit about Grid United, you might not have heard of us. We're a relatively new company, founded a little bit over 2 years ago. We have 42 people at the company, so we're relatively new and we're relatively small, but we have a really great team of experienced power industry professionals. And what we have is a big vision, interregional planning approach, where we're focused on interregional ties, grid-to-grid ties, not gen ties. We're trying to do what our name says, unite the grid. And when we talk about those interconnections, the Western interconnection, Eastern, and ERCOT, how do we find those economics between the different zones? We need to right-size the lines. We need to make sure that we can repurpose the existing infrastructure we have. We have a stakeholder-first approach, and what that means for most of the people at Grid United, they're out there talking to landowners. They're in the communities. They're holding the open houses. They're doing the permitting, and that's really the majority of the work that Grid United's doing. For me, I'm using a stakeholder-first approach when it comes to utilities. We're out there talking to a lot of the utilities in the country, RTOs, ISOs, and when I go through the interconnection studies with them, getting the feedback from those utilities is so important to me, to be able to know what contingencies we're planning, to understand their systems. I come from a background of transmission planning at a utility. I started my career at Central Hudson Gas and Electric in New York State, doing mostly transmission planning. So working with transmission planners to try to understand how to incorporate interregional lines is so important, because what we're trying to do really spans beyond what one utility can do. And we're building utility partnerships. One of our main utility partnerships is with Elite for our first project here. I'll go through Grid United's project portfolio starting from the north. We have North Plains Connector, which is a 3 gigawatt HVDC tie from the WEC in Montana from Colstrip, and you'll see it breaks off as a Y. It will interconnect to MISO to the north and SPP to the south. So this will be one of the first lines in the country to bridge 3 different zones, and the 3 gigawatts will be bidirectional, be able to send those resources back and forth. Wyoming Intertie, a small line, only 100 miles long, so it's HVDC, possibly AC due to some of the graphs that Henry showed, some of the economics, but a very important line nonetheless. Wyoming Intertie, we also call it YTie, will connect SPP to the west. A lot of these lines are connecting SPP to the west. As I said, we're looking to bridge the gap between the Eastern Interconnection and the Western Interconnection, this one connecting to Pacificor. Relay Intertie, another one bridging that gap, coming from Nebraska to Colorado. Three Corners Connector, going from Colorado down to Oklahoma. That's a 3 gigawatt project. We are working with SPP. We've gone through the feasibility studies for Three Corners and North Plains and gotten acceptance of the feasibility results to date. So now we're moving on to the planning phase and looking to do the dynamic analyses. Continental Connector, the next one moving south down all of our projects that we have at Grid United. It's in early development stages, but we'll connect PNM in New Mexico to Kansas. Moving down to trying to connect the interconnections, and ERCOT, Pecos West will connect into ERCOT and into El Paso Electric. So I probably rallied off 6 to 10 utilities that I'm already working with different interconnection filings I have. And it's a lot of work because I'm trying to keep everybody, keep it all. We had a lot of balls up in the air trying to figure out where those filings are. So those are our HVDC ties. We also have some AC high voltage lines. South Line is a project that Grid United is a co-developer, and that has been developed for over a decade now, but it's in a very important part of the country where if you see the Lawrence Berkeley National Labs reports showing that in 2021, the value of the different corridors, this one is placed in a place that, really would benefit from different interregional extreme weather events and so forth. And last but not least, Valley Power Connect, also known as North Gila Imperial Valley 2, is a approved project by the CAISO board that Grid United has bid into. So when I look at all of this, right, it's wild right now, right? I started in the utility industry in 2001, and load growth was, I would say, slow and steady. At the end of my decade at the utility, I ran some energy efficiency programs with the New York State Department of Public Service, and I really feel like energy efficiency for the last decade, this is my opinion, not Grid United's opinion, it's sort of flattened the load growth in the country. But now that's not the case. Elon Musk, a couple of months ago, I think we all know who Elon Musk is. He gave a speech to the Edison Electric Institute, all the utility CEOs in the country, and said, you guys are underestimating how astronomical load growth is going to be. And it's not just to plug in Elon's Teslas, it's also artificial intelligence. One of my best friends works at Google. He designs data centers for Google. He started in 2018, and the rage there was the cloud. He built a bunch of data centers for the cloud. He has told me for AI that data centers are going to be 5x the demand that the cloud was. There was an article, and if you don't believe me, there was an article in the New York Times a couple of weeks ago just talking about how much demand AI is going to take. Are we ready? I hope so. We see a lot of articles out there that are pointing to the benefits of interregional planning. There's been a lot of studies out there that point to the interregional planning. I could rally off a bunch of them. I'm going to quote some of those studies today. But we see articles in the New York Times, Wall Street Journal saying we need to 2x, 3x the grid. And I think Rob Gramlich of Grid Strategy showed a slide yesterday that, you know, the graph of transmission development, transmission build out in the country is basically flattened out. In 2013 was we hit a peak, and now we haven't really built anything. So how are we going to do this? Well, we got to bridge the gap, and also at the same time, we need an all of the above approach where it's everything. We need it all. We need nuclear, geothermal, coal and gas with carbon capture, onshore, offshore wind, seeing that 20 gigawatts. I did a year in the offshore wind industry, and seeing the 20 gigawatts on the CAISO slide makes me very happy because, and seeing how we're building out the grid. And that's one of the things that I realized when I was in offshore wind is that there is no grid really for that in a lot of the places in the country. So how do we build out the grid along the coast is another big item that, you know, people need to look at. I showed the slide. Most of our projects are in the center of the country because we see the benefits of interregional lines. I'll go through this. More benefits of interregional lines, right? Henry did a really great job. We break it into two buckets. This diagram is from a Brattle Group report with grid strategies in 2021. We have reliability and resiliency benefits. That's one bucket. For me, improved grid operations utilizing HVDC capabilities. If anybody was at the HVDC tutorial on Monday, Johannes and Chandra, Johannes of Brattle Group and Chandra of DNV went through a report that Grid United sponsored that came out last month. It's a great report. I tell everyone, look at it. It's kind of my guidebook. There's a lot of great examples around the world in Europe of the different applications. And applications are endless, talking about frequency response, black star capabilities. So I really push people to try to look at that report. When we look at what's in between, well, we talked about the extreme weather events. Henry went through those. And when I look at extreme weather events, what we really need to do is build the grid bigger than those events. I'll quote another report from Grid Strategies in May where they took a look at the last 5 major winter storms or hurricanes and storms. Winter storm Uri and Elliott were both in those. And it basically shows that when these extreme weather events hit us, they're somewhat regional. It's not going to hit the whole country, but that's where the grid comes in. If we build the grid big enough to be able to weather the storm, no pun intended, and be able to help one part of the country to the other part of the country, that's where those benefits really come in. And the economics part of it, as I said, those low probability events, reduce ancillary costs, and so forth. This is a value stack that Jackson, my colleague from Grid United, did for us. And it talks about market efficiencies as one of the big chunks, this green chunk over here. Production cost savings. I'll quote another study. Sorry, I'm throwing out all these studies. If you need to know any of these sources I'm throwing out, I'll get with you, give you my card. They had a study, actually, ESIG had a webinar about this. Johannes spoke at it about intertie optimization. And right now, it's not optimized, and it's kind of eye-opening, some of the examples that Johannes gave during that webinar. So go back. It was at the beginning of this month if you want to watch it on the ESIG YouTube. So that's a big chunk of it, the market efficiency. We talked about the reliability and resiliency, the interregional transfer, new resources being added, the extreme weather events, utilizing transmission in a more optimized ways. And then there's additional benefits. We talked about Black Star, ancillary services. Voltage control, to me, is such an important thing, the dynamic reactive support that HVDC converter stations can provide. So those are the benefits. I tell you a little bit about Grid United. Now I was going to tell you all about the challenges, and there are challenges. So with great benefits come great challenges, and I'm trying to quote some of the speeches that we saw in the last few days. Multi-value planning, another one that Rob Gramlich of Grid Strategies talked about. We don't have that multi-value planning process in place yet. This happening. AMO is doing a really good job with that. In Europe, NSOE is doing a good job with that. So we could learn from the experiences across the globe to try to bring those planning criteria and those planning processes, that multi-value, to take all these benefits and really understand them from a benefit cost perspective when we look at interregional lines and HVDC lines. A lack of robust interregional planning. You know, I'm really happy to see the NERC study. I'm excited about that because it is forcing this interregional planning to really happen. We see a lot going on with SPP and MISO. I'm in the Northeast, so NISO with ISO New England and PJM, it's starting. We see it starting, but developing that robust interregional planning and beyond just two regions. Some of our lines, as I said, fill the gap between 3 different regions. So how do we actually understand how we do that big interregional planning? Not to quote Rob Gramlich again, but we talked about the silos of resource adequacy and transmission planning. That's something that I know ESIG has a lot of working groups that are looking at that and trying to understand. They've operated in silos for my whole career. So we're trying to understand that. And you know, the existing interties really not being optimized is a real major place that we need to look at. The planning paradigm is changing. You know, I say it again, back in 2001 when deregulation hit, my first project, I'll give you a little story. They sat me down in my new cube and they dumped 200 size D and size E prints. I had these vellum prints from 1950. And they said, deregulation has happened. We have to, Central Hudson sold off their coal and natural gas power plants along the Hudson River. And they said to me, well, we got to split our substation apart from the generating station. So you're going to go through all these wiring diagrams and all these schematics and figure that out. I said, okay, great. So I got thrown right into the industry when deregulation happened. But that's how it was 22 years ago. It was a vertically integrated utilities, and you had synchronous generation, and you served load. It was localized. We don't have that anymore. We have geographically diverse, weather-dependent, small-size resources. I'll point to Henry's slides, and his maps did a much better job than I can try to say up here. So just think of those maps that Henry had up before. We also just don't have planning methodologies that, you know, are looking at network constraints right now. Everything's kind of intra RTO at this point. We don't have a lot of the inter-regional stuff going on. And for me, that last bullet, the current HVDC VSC interconnection studies. I'm in charge of all the interconnection studies, working with a lot of consultants, a lot of them in this room that are doing the great work to try to make this happen. So I commend everyone that's trying to work to figure this stuff out. But with HVDC, VSC, voltage source converters, it solves a lot of your problems on the grid. And in the past, when I worked at GE for 11 years, 7 of it working on onshore wind farm grid integration. And we do filings with all the developers in this room pretty much. And It was always sort of a, what is this generator going to do to the system? Oh, you're going to break the system if you put this wind farm in. That's not how it is with VSC, HVDC. It has the capability to do the frequency response, power oscillation damping, and all these great applications that I'm really looking forward to getting into the dynamics and PSCAD studies. And on that note, what about the models? Modeling is obviously going to be a challenge for us. Right now, we talked about it, the models can't capture routine weather volatility and extreme weather scenarios and really value them in the right way when it comes to production cost modeling. And then on my side of the house, looking at interconnection modeling, I'll use an analogy that if you saw Kelsey Chimney's speech, my colleague, on Monday, talk about the precision of the studies and when you need them and when you time them. If you can hand tighten a nut on a bolt, or if you need a torque wrench, when do you use the tools along that process? Because leading into my last challenge, the fourth challenge here, we don't have enough engineers, and I don't know if it's come up enough during these presentations. I look at this as the #1 challenge to our industry. So how we utilize our resources is just so important right now, and timing the studies along the route to make sure that resources are being used when we really need them, and not doing studies just for the sake of doing studies. For me, in particular, you must think I'm crazy. I have all these projects up here. We haven't selected any vendors yet. So for us to get on doing some PSCAD models without having the converter source codes and so forth, converter black box models, and not knowing what vendor, that's not really, we're not ready for that yet. So timing it is very important. I see some laughs. Maybe it's because the second bullet, oversupply of non-engineers with opinions on planning and building more transmission. And this was something that I said I was in the offshore wind industry for a year, and I went to a lot of conferences and I was on panels, and everybody would stand up and be like, we need more transmission. And I was like, all right, well, what's happening? And I look at the people in this room that are the ones that are really making the solutions. We need more people that are coming up with the solutions to these problems. We need more people that are working on the supply chain issues. Obviously, HVDC converter stations, you can't get them until like 2030, 2031 right now. There's only three major OEMs doing it. So how do we build out that supply chain? So those are the challenges, and the people in the room here are gonna figure it out, I hope, because who else is gonna do it? We gotta do it here. So last but not least, a quote from President Eisenhower. And this is kind of fitting because President Eisenhower in the 50s, they did the Interstate Highway Act. And when we look at what we're trying to do here, this macro grid, they call it, it's an interstate highway of power lines, if it's AC and DC, but we're trying to build that out. But what did President Eisenhower say? He said, plans are useless, but planning is essential. So the key thing with that, what that means to me is, we're planning, but we got to be nimble, and we can't be boxed in with our plans. We have to have flexibility in what we're doing along the way. So I look forward to getting more involved with ESIG. As I told Charlie, Nick Miller over there, Charlie came to Schenectady when I was at GE 7, 8 years ago, and Nick said to me, Mike, you need to get more involved with ESIG. I always remember that. And I said, oh, I'm so busy and I got no travel budget, so I could never do it. But now I'm here and I'm looking forward to getting involved with some of the working groups and so forth. So thank you so much.